In standard sophomore electrical engineering circuit theory, we always analyze electrical behavior using a perfectly idealized instantaneous model. But this model completely ignores the physical reality of high-speed digital design. When we push signals into the high megahertz and gigahertz range, standard schematic analysis fails, resulting in complete signal integrity collapse. In the field of electromagnetic compatibility, or EMC, the physical length of a trace, measured in inches or centimeters, is analytically useless. To accurately predict a circuit's true behavior at high frequencies, we must measure its electrical dimensions, a ratio of the object's physical length to the electromagnetic wave traveling through it. Relying on physical dimensions and ideal schematics is the primary reason engineers fail EMC compliance testing. The core flaw in ideal circuit analysis is the assumption that a voltage change at the source instantly appears at the load. In reality, electromagnetic waves have a finite propagation velocity. They actually take a measurable amount of time to travel down a conductor. These graphs show the input sine wave I1 of t at the source and the delayed output sine wave I2 of t at the load. Because the wave takes time to arrive, there is a measurable phase shift between the 2 points. The physical length of the connection lead directly determines the magnitude of this delay. As the frequency of the signal increases, the wave cycles faster. That means this fixed physical time delay creates an increasingly larger phase shift. When this phase shift becomes significant, the wire acts as an active component, actively altering the signal. To quantify this phase shift, we use wavelength, denoted by the Greek letter lambda. Wavelength is the exact physical distance a single-frequency electromagnetic wave must travel to change phase by 360 degrees. This diagram shows wave propagation over distance c. The full cycle defines 1 lambda. Its length is governed by a simple equation. Wavelength equals velocity divided by frequency. As frequency escalates into the gigahertz range, the distance required for a phase shift shrinks drastically. Calculating this exact wavelength is the mandatory first step before analyzing any printed circuit board layout. Electromagnetic waves only travel at their maximum velocity, the speed of light, in a perfect vacuum or free space. In physical printed circuit boards, copper traces are surrounded by non-conductive insulators, known as dielectric materials, like FR4 epoxy glass. This shows the dielectric penalty. Top, a wave in free space travels at maximum velocity. Bottom, in a dielectric medium, it's slowed by the square root of epsilon r. Velocity drops, so wavelength must compress. In FR4, permittivity is 4.7, cutting wave speed by half. Embedding a trace inside a PCB dielectric mathematically guarantees it will become electrically large at a much shorter physical length than it would in open air. There is a hard mathematical boundary that separates simple circuits from complex transmission lines. It is known as the lambda over 10 threshold. Here, a circuit component scales against a sine wave. An electrically small circuit is strictly less than 1/10 of a wavelength. Below this boundary, phase shift is under 36 degrees, making Kirchhoff's laws valid. Exceeding lambda over 10 crosses into transmission line physics, governed by Maxwell's equations. This diagram shows the result of crossing that boundary. The ideal wire breaks down, transitioning into distributed lumped pi and lumped T equivalent circuits, which introduce parasitic resistance, inductance, and capacitance. The lambda over 10 rule is the definitive test. It dictates exactly when you can trust your schematic and when you must design for transmission line effects. To see how this dictates physical design, we run these formulas through a 3-step mathematical stress test. This calculation shows a baseline test for a 600 MHz signal propagating through an FR4 board. First, we factor in the dielectric penalty of 4.7 to find the velocity. Then we divide that velocity by the frequency, yielding a wavelength of exactly 23.1 centimeters. Now apply this workflow to a second scenario, a 5-centimeter wire suspended in open air, carrying a 250 MHz signal. Because it is in open air, the wave travels at the speed of light. Dividing that velocity by 250 MHz gives a wavelength of 1.2 meters, or 120 centimeters. Finally, we divide the physical length of the wire by the wavelength to find the electrical dimension ratio. 5 centimeters divided by 120 centimeters equals 0.042 lambda. Because 0.042 is significantly less than the 0.1 threshold, We confirm this wire is electrically small. It's safe to treat as an ideal component. The danger appears when we apply high frequencies to physically tiny traces, like a standard 2-inch or 5.08 centimeter connection on a board. Consider aggressive operating conditions, a 2 GHz clock speed routed through an FR4 dielectric medium. This calculation shows the wavelength for these specific conditions. At 2 GHz, the frequency is so high and the dielectric penalties so severe that the wavelength compresses down to exactly 7.5 centimeters. Step 3 sets up the final electrical dimension ratio, physical length divided by wavelength. We divide the trace length of 5.08 centimeters by the compressed wavelength of 7.5 centimeters. The resulting electrical dimension is 0.677 lambda. That ratio massively exceeds the 0.1 threshold. At 2 GHz, a mere 2-inch trace is dangerously electrically large. This dictates an actionable workflow for all future designs. First, check your frequency. Second, check your dielectric's relative permittivity. Third, calculate the length-to-wavelength ratio. Physical size is an illusion. Only by calculating electrical dimensions can engineers prevent signal integrity collapse and survive electromagnetic compatibility testing.